and thanks for giving our second seminar.
Okay, so hello from my side as well. Thanks for the introduction. Today I will focus on the catchment scale and the multi-decadal kinematic development of glaciers. Therefore, I will first introduce our two catchments, the study, and then report a bit on the methodology, and then present the results, focusing on common trends, but also on the differences in development, and show several examples. Okay, first I want to introduce the CEHAP project within which the study was conducted. This project aims to provide an understanding of effects of climate change on high alpine geosystems since the Ice Age, following an interdisciplinary approach. As you can see here, many different universities are involved and many disciplines. Yeah, so as our study is catchment based, I of course want to introduce our two catchments. They are both located in Austria in the Ötztaler Alps, and they represent two of the three catchments that are investigated by the CEHAP project. The Hollachtal has an area of about 60 square kilometers and an elevation range about 1,500 3,300 meters. Kaunertal shown here, larger in area, a little higher in elevation. Yeah, so as a first step, we manually mapped all the rock glaciers that are present in the catchment. Did this on the most recent orthophotos and hillshade that are available for the catchments. We then classified the rock glaciers according to their activity status based on flow velocity and elevation changes. Yeah, these were analyzed using the most recent digital elevation models that we have available. We further analyzed, classified the rock glaciers based on the connection to the slope unit. Yeah, to give an impression of the rock glaciers we studied, I plotted some of the characteristics like the minimum elevation, the aspect, the area, and the upslope unit in this whole diagram. The studied rock glaciers range in area from about 7,700 square meters at this rock glacier to 0.2 square kilometers this rock glacier. As you can see, they are rather north exposed and show a minimum elevation, so the elevation at the rock glacier front about 2,300 meters this rock glacier to 2,700 this rock glacier. Yeah, while the Hollachtal only contains talus connected rock glaciers, have talus and glacier forefield connected glaciers. In order to analyze the changes in dynamics over several decades, we used a variety of data, as shown here in this timeline. From the early 1950s onwards to the end of the 90s, used aerial images. And from 2006 onwards, we used ALS data. The ALS data of 2006 was recorded by the government, while the more recent ALS data from 2012 onwards were by ourselves, as you can see here. Yeah, so now briefly some words about the processing of the data to derive point clouds, so elevation data and orthophotos. From the aerial images, we used Agisoft Metashape and used for this purpose the film camera option and used parameters from the camera calibration protocols. And this proved to be quite important to achieve good results for point clouds. To derive information on the horizontal displacements, we used both orthophotos, aerial images, and the hill shapes from the ALS data. And as a first step, we co-registered them. Then we used the image correlation algorithm ImCore that's implemented in RGIK to derive the displacement vectors. We then filtered these vectors manually and also did an error assessment of table errors. Yeah, in order to obtain information on the vertical displacement of the rock glaciers, we processed both photogrammetrically derived and ALS point clouds. Yeah, this pre-processing step mainly consisted of the alignment of the point clouds. We then gridded the point clouds and calculated differential elevation models. And we used these to get information on the surface elevation and the volume changes of the rock glaciers. So yeah, on this slide, we can see the results of the flow velocity analysis. Figure shows the flow velocities of the individual glaciers from 1950 to 2017 and 2019 in Hollertal as box plots. Yeah, as can be seen, the mean flow velocity of the rock glaciers is mostly well below half a meter per year during the entire study period. The maximum flow velocities, which was most of the time recorded at the terminal parts of the rock glaciers, is in parts quite faster. The fastest flow velocity was measured on Hollertal 1. That was the one that was shown in the first slide on the picture. And here the maximum flow velocities are well above 1 meter and parts even above half meters. What can also be seen, as in many other studies in the European Alps, is an acceleration in the time step 1997 to 2006. And this suggests an acceleration in the late 1990s. Despite this general trend, the magnitude and spatial pattern of the changes in flow velocity vary considerably between the rock glaciers. So in the following, I want to show some examples to underline this. So these three rock glaciers shown here show a transition from transitional state, so movement rates below 10 centimeters per year, to an active state, while the acceleration here in this case of Hollertal 5 is very small and only occurs in the most recent time step, while on the other two glaciers the relative acceleration is up to a factor of 5. here in this example, we see the rock glacier Carnotile 7, which showed area-wide flow velocities less than 10 centimeters until 1997. And from this time onwards, it accelerated and showed flow velocities of more than 50 centimeters. This area of the we can observe the different magnitude of acceleration also on rock glaciers which were already classified as active before the acceleration. Here we see two rock glaciers, Carnotile 1 and Carnotile 1, which show low and high relative acceleration in the time step 1997 to 2006. And while on Carnotile 1, the mean flow velocity increases by a factor of 4 between the first and the last time step. On Carnotile 1, there's only very small acceleration between the first and the last time step. See the rock glacier Carnotile 1, and although we see variation in the flow velocities, especially in the terminal part of the rock glacier, flow velocity when first and the last time step is compared is quite similar. Yeah, this is the example of Carnotile 4. This is a rock glacier which showed no acceleration or even slight deceleration during the investigation period. This rock glacier is characterized by a pretty low slope angle, high ice content, and it presumably formed from a bush moraine. The example, and although we here as well see variation in flow velocity at the terminal part of the rock glacier, and also can see an acceleration in the 1990s, the flow velocity decreases actually in the last two time steps. As a final example, I want to show KT 08. That's a quite interesting example because it shows a disintegration and an inactivation of the terminal part at the beginning of the study period. That's quite interesting because we usually hear about destabilization and disintegration of rock glaciers in more recent times. So here we see the example, and here the morphological evidence indicates that the disintegration took place even before 1953. And then in the first time step, we see here the flow velocity is missing because of the image correlation wasn't possible due to decorrelation. But we can see very high flow velocities, or very high, but flow velocities well above 1 meter until 2006. And then, like here, the blue colors, almost no horizontal. Yeah, so although we could not really identify characteristics that explain these different reactions, we explained the different development of flow velocities by different sensitivity or response time to changes in external forcing. And that's probably caused by a different internal structure and different topography of the individual rock lake. Besides the development of flow velocity, we also investigated the surface elevation changes of the rock glaciers. And as shown in the DOD on the right here, the mean surface elevation change is a balance of both positive and negative values. So these are reflecting, among others, the downslope movement of the rock glacier, the compression and extension, and the melting of excess ice. In this example, the volume balance is around minus 10,000 cubic meters per year, and this translates to a mean surface elevation change of minus 4.5 centimeters per year. And this mean surface elevation change is shown here for all the time steps and all the rock glaciers. So as can be seen in the figure, the mean surface elevation change of the rock glacier ranges between around 0 and just a few centimeters per year. The studied rock glaciers show a clear tendency towards negative volume balances. And as the negative values predominate in the balances, this clearly indicates a melting of excess ice or a compaction due to loss of pore spaces. Although I didn't mark them here, these negative values are more pronounced on rock glaciers that are connected to glacier forefields than on talus-connected rock glaciers. Yeah. As can be seen, the magnitude of the increase in negative values varies from time step to time step, but at least in the countertal, so these are these rock glaciers that are marked with KT, the negative values increases from time step to time step, and this phenomenon is not that clearly visible in the countertal. Okay, so as we saw in the figure on the slide before, so the mean surface elevation changes, there are quite some different patterns of this surface elevation change on the rock glaciers. So some rock glaciers, as shown in these examples here, show hardly any surface elevation change in the first time step and also don't show any flow velocity above the detection level in the first time step. In the following, they show negative and positive values. But as you can see on these figures here, these positive and negative values, they result in balances close to 0. So yeah, these were the rock glaciers where we measured a strong relative increase in flow velocity as well. And what is striking here is that these are the smallest rock glaciers we studied. Another pattern we saw is that of rock glaciers which show balances close to 0 in the first time step and then showed increasingly negative values, especially from 2006 onwards. And this can be seen in this example here. But, and that's important, most of the investigated rock glaciers show the pattern that is here shown in these two examples. That is, positive and negative values throughout the investigation period, but these positive and negative values lead to negative surface elevation changes that are increasingly, that increase, like shown here and here. So in addition to just describing the temporal changes in rock glacier kinematics in the two catchments, we also made a qualitative analysis of the external forcing factors. We used existing literature to link the development of the forcing factors to the development of the multi-decadal kinematic evolution of the rock glaciers. On these two plots, you can see the annual precipitation, the mean annual air temperature, and on this one, the snow cover onset and end. And these are analyzed for stations that are nearby the countertime. Yeah, so during the period of investigation from the 50s to today, we can observe, of course, a significant increase in temperature and a significant decrease in the end of snow cover. And yeah, looking at time, I don't want to go into detail here, but the significant decrease in the end of snow cover leads to an earlier availability of liquid water and an earlier influence of air temperature on subsurface temperature. And in addition to the significant increase in air temperature, this presumably leads to a change in the flow properties of the permafrost body due to the warming of the permafrost ice and an increase in water availability, which leads to which influences the water availability influences the movement in the shear horizon of the rock glaciers. So I'm almost at the end of the presentation, and in this slide want to briefly summarize the presentation. It can be said that the combination of the historical aerial images and the ALS data is well suited to detect flow velocity and surface elevation change of rock glaciers back to the middle of the 20th century. In general, the measured flow velocities were in good agreement with other studies in the European Alps concerning the magnitude and also the timing of acceleration. The mean annual surface elevation changes of the rock glaciers range between 0 and a few centimeters per year and show an increasing trend on most of the studied rock glaciers. And this, as we discussed before, indicates a progressive thaw of excess ice. Yeah, despite these general trends, the catchment-wide view also shows that magnitude spatial patterns of the multi-decadal changes in the kinematics of rock glaciers can be quite different, and therefore it might be of value and interesting to integrate historical flow velocities and surface elevation changes into standardized rock glacier inventories in order to better understand their different reactions to climate change. So this is already the end of the presentation, and I want to thank for your attention, and of course also thank my co-authors and colleagues. Thanks.
Well, thank you very much, Fabian, for the presentation. It was very nice to see this study site and all your results in detail. So now we can open the room for questions of the public, either on the chat or if you want, raise your hand. And I will stop to recording the presentation as well.